Hey everyone, welcome back, and today let's solve Leetcode problem 3108, titled Minimum Cost Walk in Weighted Graph. So just a quick FYI before we actually begin the video. This is probably going to be quite a long video, one of my longest, if not the longest videos, because it is a pretty lengthy problem. It does also have a pretty lengthy solution in terms of code, and so yeah, feel free to just fast forward or just go to the part that you want to see, whether it be the explanation, the code, the walkthrough for the examples, and whatnot. But just a quick FYI that this would be a pretty long video. I would estimate about 30 minutes or so. I could be off, but that's what I kind of want to say that the length of the video would be. So let's go ahead and get into the problem here. So there's an undirected weighted graph with n vertices labeled from 0 to n minus 1. And we're given the integer n and array edges, where edges at any index I is going to have a length of 3. U sub I, V sub I, and W sub I. That's going to indicate that there is an edge between vertices U and V, and they have a weight for that specific edge of W for that index I in the input array edges. So a walk on a graph is a sequence of vertices and edges, and it starts and ends with a vertex. And each edge connects the vertex that comes before it and the vertex that comes after it. It's also very important to note that a walk may visit the same edge or vertex more than once. We can reuse the same edge more than once for a specific walk. Now, the cost of a walk starting at node per se U and ending at node V is defined as the bitwise AND of the weights of the edges that we actually traverse during that walk. So in other words, if the sequence of edge weights encountered during the walk would be W sub O, W sub 1, up until W sub K, the cost of that walk would be calculated as W sub O bitwise ANDed with W sub 1, bitwise ANDed with W sub 2, and so on and so forth, bitwise ANDed with W sub K, where the AND operator is simply going to denote the bitwise AND operation. We're also given a 2D array query where query at index I is going to be equal to S sub I and T sub I, and for each query we need to find the minimum cost of the walk starting at vertex X S sub I and ending at vertex T sub I. However, if there exists no such walk, we have to have an output of -1, where effectively we're really just trying to answer this query's array for every single S and T for those specific vertices. Now we want to return an answer array, and of course the answer is going to have the same length as our input query, because we're going to answer each query exactly once, and answer at I obviously is going to denote the minimum cost of a walk for query I. So in example 1, we have our input n to be 5, and our edges to be 0, 1, 7, 1, 3, 7, and 1, 2, 1. Keep in mind the edges simply mark the edges between which nodes and their corresponding weight, right? That's the whole point of the input edges, right? Now, whatever the reason why we have an input n is in the context of example 1, we have 5 unique vertices, as we see up here. We have 5 vertices labeled from 0 to 5 minus 1, or in other words, 0 to 4. So in this case, the reason why we have an output of 1, -1 is basically 1 would be the answer for the minimum walk for the 0, 3 vertices, or the initial query, and -1 would be the minimum cost of a walk for the query, technically at the second, or the first index, right, for 3, 4, between these two vertices, 3 and 4. And the reason why that is the case, well, because the reason why the cost is 1 for the initial query is because we need to actually move on to the following edges, right? We'd go from 0 to 1, then we'd go from 1 to 2, then we'd go from 2 to 1, then we'd go from 1 to 3. That's going to have a weight of 7. In the second query, though, there is no walk between nodes 3 and 4. That means it is impossible, or there exists no walk to actually go from vertice S to vertice T, and so that's going to be an output of -1, meaning it's kind of invalid. So in example 2, we have our input n to be 3, and our edges to be 0, 2, 7, 0, 1, 15, and 126, 1, 2, 6, and 1, 2, 1, and our query in this case is going to be 1, 2, right? In this case, we have an output of exactly 0. Why is that? Well, because to actually achieve that cost of 0 for our first query, we actually first need to move onto the following edges, right? We go from 1 to 2, then their path would look like 2, back to 1, and then 1 to 2. That would be a weight of 1, a weight of 6, and a weight of 1, respectively, right? That's why we have an output of 0 for the query 1, 2, right? Of course, it's going to have a length of 1. Why? Because we only have one query, or basically one pair of vertices S and T, going from 1 to 2. Notice our path is going from 1 to 2 with those specific weights 1, 6, and 1. So for the constraints here, we see that n is going to be within 2 and 10 to the 5th power. The length of our input array edges is going to be between 0 and 10 to the 5th. And any value at edges is always guaranteed to have a length of 3, having 3 different elements. So it is always going to be valid, like the problem told us. And any node u and v is always going to be between 0 and n minus 1, again guaranteeing that it's valid. U is not going to be the same node as v. W is always going to be between 0 and 10 to the 5th power. Again, that's just keep in mind the cost or value for the specific weight of u and v, nodes u and v, that is. The length of our input array query is going to be from 1 to 10 to the 5th power, and any value in the query is always going to have exactly 2 edges. We're guaranteed that, or 2 vertices rather, and s and t are also always going to be between 0 and n minus 1, and the vertex s is never going to be equal to the vertex t. Again, it's just guaranteeing and confirming what the problem statement told us and telling us that we're not going to have any weird edge cases or any invalid inputs to deal with. So with that out of the way, with that very long example and that very long problem statement, let's go ahead and look into how we can actually solve this problem efficiently. And that brings us to the kind of high-level algorithm that we're going to be using. We're actually going to kind of use a combination of the union find data structure, and I'll actually comment that out as well once I'm done kind of explaining it. It's called the union find data structure. It's also known as the DSU, which I believe stands for I don't remember, I think disjoint set union or something like that, right? And also we're going to be using the bitwise operations because, of course, we want to actually calculate the bitwise AND of all of the weights that we use for each walk to answer our queries, right? That's the whole point of the bitwise AND operator here that we see with this symbol. Sorry, take a while for me to kind of find it on my keyboard. And let me actually quickly comment that out. We're going to be using the union find. I'll actually put a, I don't remember what it's called. Data structure, also known as the DSU. I'm not going to type out disjoint set union. I think it's just too much work for me, so let's just forget about that. Okay, or the DSU data structure. Perfect. So how are we going to use this on a high-level rundown to solve the problem? Well, initially, we're going to initialize our union find class, right? So we're going to have a union find data structure to actually group the vertices into connected components. That's the whole point of that data structure, and that's very, very, very important in actually efficiently determining, well, are 2 vertices connected and merging those components, right? And for the actual bitwise AND operation part of this solution, as we actually merge those connected components, we're also going to maintain the minimum cost. We're going to try to minimize the cost and optimize it for each component by performing those bitwise AND operations on all of the weights W of all of the edges within that specific connected component. Right, kind of like within that specific walk, if you will. And then, of course, once we actually initialize the class and get into the solution part, we're actually going to, answer the queries or process and answer the queries. So for each query, we're actually going to check if the 2 vertices belong to the same connected component. And if they do, well, then the stored minimum cost for that component would be the answer. And otherwise, we just have an output of -1 for that specific query. So let's go ahead and get into the actual solution for this problem, right? And just a quick FYI, it is in no way a simple solution, at least in terms of code. There's a lot going on, and so what I'm first going to do is actually initialize my union find class. So as you may imagine, I'm just going to call it union find. I don't know why I always mess up the spelling for this. It's really a simple spelling. And in this case, we're going to have a couple of different methods here. The first one is, of course, our initializing method, right? We need this initializing method to actually, initialize the object of this class. When we actually initialize the objects of the class, which we will do in the solution class, and in this case, of course, we're going to have an initial parameter of self. This is, of course, object-oriented programming, and we're also going to take in a parameter n. Notice how n is the same thing as we have in the solution class, right? And in this initializing method, of course, when we actually initialize the object, well, let's actually initialize all the data structures and the variables that we need to use to solve the problem. The first is the parent, so I'm going to call it self.parent. This is what I'm going to call it, and it's going to be initialized to the list of the range of n. If n was 5, it'd be a list of 0 to 4. If n was 10, it'd be a list of 0 to 9. A range is simply just calculating all the integers between that range from 0 to n minus 1, right? And of course, it's going to be initialized as a list for all those values. Once we get the parent, we'll also get the rank, so I'm just going to call it self.rank, and it's going to be initialized to all zeros and have dimensions of n for all n values. And of course, we're also going to initialize, self, looks like I can't spell today, or type, so it's going to be min cost. Right? Oops. And as this may imagine, it's going to be initialized to all -1s, and it's also going to have the same exact dimensions as n. So on a high-level rundown, what are we really doing here with this separate union find class? Effectively, once we initialize it and actually get the initializing method to initialize our data structures, self.parent is going to be a list of a range of n. It's going to be a list where each index is going to represent a vertex from the range of 0 to n-1 for all n edges, right? And now, rather for all n vertices, right? And the value at each index in that range would represent its parent. So initially, each vertex is going to be initialized at its own parent, rather as its own parent. That's how it's initialized to, and that's the whole reason why we call it self.parent for that specific list. And for the actual self.rank purpose, the reason why we even have this is, again, it's still a list of all zeros of dimensions n. It's going to track, or rather kind of confirm or keep track of the depth of each tree for union by rank optimization. And the reason why we have this min cost list is going to be a list to actually store the minimum cost, which is again calculated by the bitwise and of all row weights for that specific path or walk for each merged component. And we're going to initialize them to all -1 because that kind of indicates or simulates that no edges have actually been processed yet. So in this class, once we actually initialize the initializing method, now let's get the find method like we usually do for DSU problems or union find problems, right? So again, it's still going to take in self as a keyword parameter, and it's also going to take in u as another parameter. Right? And basically, we're going to actually locate the representative root of the set that contains vertex u, but more on that later, right? So once we actually get the two parameters self and, of course, u, now we're going to have a quick conditional here. If self.parent at this specific node or index u, if it's not equal to u itself, well, then we want to update self.parent at u, and it's going to be equal to self.find, kind of recursively calling this find method in this initialization, right? Self.find of self.parent at the specific index u. Sorry, it looks like I completely butchered the spelling here. Now, if that's not the case, though, we just want to return the self.parent. Rather, not if that's not the case, but we want to return self.parent at u. Now, what are we really doing here in this find method? Effectively, we're actually locating, again, the representative root of the set that contains that specific parameter u as our vertex. Now, if u is not its own parent, how it was initialized in the parents method, if it was actually changed, meaning it's not equal to u as a parent itself, if it's not its own parent currently, then we have to actually recursively find its parent using, or rather calling self.find again recursively, and then applying that path compression by setting self.parent at that specific u to the root. And that also, this is again an optimization technique. It also does flatten the tree, and it also does lead to more efficient future operations. And effectively, once that's done, once we actually handle that logic, we simply return the root of u. So that's it for the find method here. Now let's actually initialize the union method. This is by far the longest method in this class here, so I'm just going to call it union. And in this case, for its parameters, it's going to be a little bit more, unlike we talked about in the edges input. So it's going to have, again, self as the initial keyword parameter. We're going to take in u, we're going to take in v, and you may have guessed it, we're going to take in the actual weight. This is, again, for each parameter or each weight and node uv in the edges input array, right? So it's going to be a lot of code. I'm kind of just going to be typing it out and then actually explain how it works as a whole once I'm done with all the lines of code. So kind of feel free to fast forward for a couple of seconds if you will. It's just going to be me kind of typing out all these lines of code. So let's first get root u, and it's going to be initialized to self.find. Again, we're calling find at that value u for its actual parent. And we'll also get the root of v. That's also going to be self.find. In this case, you might have guessed it, at v, sorry, not xv. Now, once we actually get that, now, if root u, for this specific node u, if it's equal to root v, sorry, there should be two O's. If that's the case, we know immediately that we want to get the self.minCost and update that. I don't know why my cursor has been quite buggy, and at least recently. So we're going to get the self.minCost list, and we're going to take it at root u, and we're going to update it to then be root v. Or rather, sorry about that. We're actually going to take root u and bitwise and it. So and equals, as you may see right here, and we're going to and equals our bitwise and operator by weight. Right? That's going to be the current weight for the current pair of nodes or vertices, u and v, in the input. Once we actually get that, then we immediately want to return for this specific iteration or for this specific call. Now, Once we've handled the logic, if the root of u is equal to the root of v, now let's actually check if the rank of those two nodes are less than or equal to each other. So if self.rank at specific or at that specific node u, if it's less, self rank, it should be root u, sorry about that. Yeah, so again, my cursor is a little bit buggy at the moment. Hope you guys don't mind that. If the actual rank of root u, so the root of the node or vertex u, if it's less, it has a smaller value than self.rank of root v, then we have to actually handle the logic for that. And the way we would do that in simple terms, we'd get the parent. Looks like my thing isn't okay. So I'll have a perfect. Now, sorry about that indentation errors. So if that's the case, then we want to get self.parent. Yeah, okay, looks like again it's really buggy. At root u, and we want to update it to be root v. Okay, once we actually initialize or update it to be root v, let's actually get self.minCost. And I'm kind of struggling with this keyboard again. At root v. All right, we're going to update it with root v. And in this case, it's going to be, again, bitwise ANDed, or I'm just going to say ANDed to kind of simplify that. Bitwise ANDed by self.min. Self.minCost at root u. All right, we're going to self.minCost at root u. And then we're actually going to AND that by the weight. Perfect. That's the conditional for if root u actually has a smaller value as a ranking than root v. However, if that's not the case, what if or else if or elif in Python, it has a larger value? So if self.rank, in fact, I can actually copy and paste that code here. What if it has a greater value than root v? Well, what do we have to do then if root u has a greater value than root v? In that case, we'll get self.parent. We'll have a very similar structure for that conditional as well. In this case, at root v, and we're going to update that to then be root u, right? Kind of very similar structure, just kind of the inverse of the other conditional. Now, once we get that, we'll still update the self.minCost. Keyboard's really fighting against me today, and we're going to update it at root u. And in this case, yeah, that looks to be syntactically correct. Sorry, it should be root u, not root at index u. Sorry about that. And yeah, that's right, root at index u. And we're going to, again, still AND it. So bitwise AND it with the self.minCost of root v. And that's going to be ANDed by the weight. And finally, once we handle that conditional, in the very last conditional, what if they're both equal? Well, in that case, it's a little bit easier. We'll simply get self.parent, or at least, not to type out, but logic-wise, at root v, and update that to be root u. And the ordering doesn't really matter there, at least in that specific context. And then we're going to get self.rank at root u. And increment it by 1. So plus equals 1. And finally, we're then going to get self.minCost and update that at root u by ANDing it, or bitwise ANDing it rather, with self.minCost at root v. And as you may imagine, that is also going to be ANDed by the specific current weight for the current pair of vertices u and I. Okay, that is it for the, union function here. And yes, it was quite lengthy. What are we really doing here? I don't want to get into it too much and kind of waste more time there. Effectively, we're merging. The whole point of this union method is actually to merge these sets that contain vertices u and vertices v based on the edge weight between them. That's why we're comparing the value between the edge weight or weight of those specific edges. Right, we're kind of merging them into be one merged component. So the way we do that is we first find the roots of vertices u and v, and if both of those vertices share the same root, we know they're already connected. And so if they're already connected, it's much easier for us. We simply update the minimum cost for that specific component by actually performing that computation that they noticed, rather than they said in the problem statement. Basically, would be that bitwise AND with the new edge's weight. However, the harder logic to actually deploy, if they're in different merged components, we have to actually merge them, right? So if they're in different components, rather, we have to actually merge the components. So the tree with the smaller rank would become a subtree of the tree with the larger rank. And if both trees have the same rank, well, then we kind of just arbitrarily choose one of them to be the new root and increment its rank where the order wouldn't matter. However, in all cases, we always have to update the minimum cost list for the new root by actually performing a bitwise AND, again, the same operation or computation, with the minimum cost of the other component and the new edge's weight. Okay, perfect. Once we actually get that, we're actually completely done with the, I don't remember what I called it, the union find class, and then we can actually get into the solution class. So here it's quite simple. We've actually done all the processing and all the logic handling. Here it's really just kind of answering and processing the array, or rather the queries. So we're first going to actually get an object of our class, or rather of our union find class, and initialize that by calling the union find class to initialize the object, and we're going to pass in as our parameter, you guessed it, n, the number of vertices we have in our current graph, in our current input graph. And now let's actually iterate through edges and call the union find union method on those specific edges, right, for all the vertices u, v, v, and their corresponding weight. So for every single vertice u, v, and weight for all of those pairs, I'll just say weight, not instead of weights, rather I'll say w, I think it's easier, in the input array edges, we're going to get uf, and we're going to call the union find. So I'm just going to call it union, because that's how I initialize as a method in the union find class. And for our parameters, you guessed it, we're going to call the current iterators, the current value u, the current vertice v, and the current weight for them. And we're going to actually apply the logic for that uf.union find, right? Uf would be your current object, and we're going to call its union method on these specific values in each iteration of edges. And once we actually get that, now let's actually initialize our result. And this result is effectively what we're going to be returning. And now let's actually answer the queries. So for every s and t, that is vertice s and t s and t, that is in the queries input array, to actually answer them, if uf.union, or rather find at s, if we know it's equal to uf.find at t, what did they tell us to do? Well, they just told us to update the minimum cost of those two vertices. So result.append for this specific query's answer, uf.minimum cost. Well, again, uf is the object of our main union find class that we initialized back on line 30, right? It's going to be uf.min cost, and for our actual parameter, it's going to be uf.find s, right? That's also going to be the index of it. And effectively, if that's not the case, if the find result of vertices s and t are not equal, we have to then add to our result a -1, indicating that this is not a valid pair of vertices for this query, and effectively just return our result. And finally, we are actually done with the entire code. I will zoom out for you guys to kind of see how much code it really is. So I probably did make some very silly syntax error here, or spelling error. So we'll go ahead and see if it's actually accepted. Yeah, okay. uf.union. Yeah, sorry, this should be weight, or this should be w rather, not weight. Sorry about that, guys. Let's go ahead and see if anything else is wrong in terms of the actual solution for this thing. Okay. Query. Okay, so it was not queries, it was query. Sorry about that. Let's go ahead and see if it works now. Probably still doesn't. Yeah, okay. Let's go ahead and see. Okay, yeah, so this should be a min cost. I don't know why I forgot my underscore there. And as you can see, now it is finally accepted, and it really is just about as efficient as you can get it to be. It beats 64% of users, roughly 65%, both in runtime and memory-wise, right? So it is really just about as efficient as you can get it to be. So on a high-level rundown, how are we solving this problem? I'm going to try to not go too complex to waste any more time. Effectively, we're very efficiently determining the minimum cost of a walk between queried vertices, S and T, by actually leveraging the union find data structure like we talked about before to actually manage and merge the connected components, and also maintain a minimum cost within each of those connected components using those bitwise AND operations as we actually computed all of the weights. And by always processing all of the edges first to always establish those components and their minimum costs correspondingly, we can always answer each query in almost a constant or big O of one time, making it a very efficient solution, at least in terms of that processing and that computation. So for the runtime complexity here, it's actually quite complex. So I'm actually, because this is a pretty large graph problem here, there's a lot of code, so I'm actually going to type it out. Runtime complexity. This is actually going to be a total runtime complexity. I'm also going to explain why that is, of m plus q. Sorry. q. Looks like I made a quick, actually no, that should be fine. M plus q, and that's going to be multiplied by a of n, where a technically has a different value. I'll get into that a little bit more in a couple more seconds. Let me just get that out of the way. Okay, perfect. That should be right. Okay, now why do we have something this complex? Let's talk about it. So, the union find operations like find and union, those methods in the class, they're going to have an amortized runtime complexity of big O of a of n. A would actually be the inverse Ackermann function, and that's going to grow very slowly, so making it also very efficient. I'm not going to get into what that really is. Feel free to Google it. I might put it in the description as well. But in addition, to actually process all the edges, that would be big O of m times a of n. And to actually answer each query, that would be big O of a of n. And so the overall runtime complexity would be big O of m plus q times a of n. M would be the number of edges, and q would be the number of queries. And again, a is that actual inverse of the Ackermann function. And for the memory or space complexity, it's actually just really linear, big O of n. And we use that space to actually store our result, or rather our lists, parent, rank, and minimum cost. So fully simplified, it's a linear runtime complexity. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.